All right, so here's some of the questions from the practice test that I think you should focus on. So in this particular problem, they give us the mean and standard deviations for cycle time and the mean and standard deviation for distance, and it asks us to do certain things with that information. So the first question says, calculate the percentile for a player who can sink a ball into a cup 9 feet away. So in this particular example, we're going to be using this mean and this standard deviation since we're talking about distance. And percentile we know is the area to the left. So first we need to find the z-score, which is going to be x. This is x. So 9 minus the mean, 6.45, divided by the standard deviation, 0.98. And that gives us 2.60. And now we need to find that in our z-score table. So the probability z, and since it's percentile, that means the area to the left. That means we could just look that up in our table. And we get 0.9953. So since it's asking for percentile, we would just round that to the nearest whole percent. Well, we don't want to really be the 100th percentile, so we're going to say a person who can sink a ball into a cup 9 feet away is in the 99th percentile. All right. Part B says, how fast do you think a player would have to stack their cups to be in the fastest 5% of sports stackers? So in this case, we're looking at this for cycle time. And then my hint is important because it says, hint, this is trickier than you think. Where would the fastest 5% be in this distribution? So remember, when we're talking fast and it's measured in terms of time, we want smaller amounts of time. So in this case, the fastest 5% is not going to be in the top of the distribution. It's actually going to be in the bottom of the distribution. So what we're going to do is we're going to look up and find the closest thing on our table to 0.05. We're going to find the z-score for that proportion. So that's going to be about negative 1.64 or negative 1.65 works. And then we're going to work backwards basically with this formula. So this formula, we have z, but we're looking for x. So we're going to do negative 1.64 equals x minus, remember we need to use these times since we're talking about cycle time, 7.85 divided by 0.95. So then here we're going to multiply both sides by 0.95 first. That's going to be negative 1.558 is equal to x minus 7.85, and then we're going to add 7.85. So that's going to give me 6.29. So for this problem to be in the fastest 5% of sports stackers, they would have to have a time of 6.29 seconds. All right, this next question is a big one where a lot of people lose points because they don't do all the work that they need to do for this problem. So in this case, we're given the statistics for two players, their speed, their cycle time, and their distance, and same thing for player B. And we need to decide who's the better player based off of their percentile. So we're not going to use this data to figure out who's the better player. We're going to calculate the percentiles for each player for each event. So one thing to keep in mind is that for speed, we want lower percentiles because faster times or lower times are more desirable. But for distance, we want higher percentiles. Okay, so this is basically going to be 4 different z-score calculations and then finding 4 different percentiles. So first I'm going to take player A, which I'll do in red, and I'm going to calculate the z-scores for speed. So we need to make sure we're using the correct mean and standard deviation. So speed, the mean is 7.85 divided by 0.95, and that gives me negative 1.95. And to calculate the percentile, we're looking for a negative 1.95, and that gives me 0.0256. So that's really like the 2.5 or the third percentile. Now we're going to do the z-score for distance. So it's going to be 7.25 minus 6.45 divided by 0.98. That gives me a z-score of 0.82. And then to find the percentile, we look for on our z-score table and we get 0.7939. So this is about the third percentile. And this is the 79th percentile. All right, so now we're going to do player B, and I'm going to do it in blue. So first, for speed, it's going to be 6.25 minus 7.85 divided by 0.95. That's negative 1.68. And when we look that up in our table, that gives me 0.0465. And then for distance, it's going to be 7.30 minus 6.45 divided by 0.98. That gives me 0.87. And in terms of a percentile, that gives me 0.8078. So this is the 5th percentile. And this is the 81st percentile. Okay, so now to determine who is the better player. Well, if we compare their percentiles, it looks like player A is definitely faster than player B, but player B can throw a further distance than player A. So in this particular example, it's not as obvious, but if we look at the actual proportions versus the rounded percentile, player A is going to be the slightly better player. So they're pretty close in terms of the distance that they can throw, 0.7939 and 0.8078. But if we compare how fast they can do their cycle time, 0.0256 and 0.0465, player A is going to be faster. So in this case, I would say I would choose player A because they are about the same for cup sinking, but player A is slightly faster than player B for cycle time. As I wrote on the answer key, based off the rounded percentiles, it's not as obvious, but on the final, it'll definitely be more obvious in terms of making that decision. All right, the next question is from Unit 5, and this is a tree diagram situation. So it says, suppose 20% of athletes use steroids. Suppose that a test is available that's positive in 95% of athletes who use steroids, but also positive in 4% of athletes who do not use steroids. First, we're going to make a tree diagram of the situation. So first of all, we're going to split up the steroid users and non-steroid users. And according to this, it says that 20% of athletes use steroids. So that's going to be 0.20. That would mean that 80% do not use steroids. Then we say that there's a test available. Well, in that test, you're either going to test positive or negative. Okay, and it tells us that the test is positive in 95% of athletes who use steroids. So that's going to be 0.95 here, which means that it shows up negative in 5% of steroid users. And then for non-steroid users, it shows up positive 4%, so 0.04, which means it's negative in 96% of non-steroid users. So in this case, we're going to figure out the probability of each situation. So across the top, the probability that someone uses steroids and they test positive is we're going to multiply that. So 0.20 times 0.95 is 0.19. And then for the next branch, steroid users where they test negative, that's going to be 0.01. Non-steroid users who test positive, that's going to be 0.032. And then non-steroid users who test negative, so 0.80 times 0.96, that's 0.768. So now it tells us what is the probability that an athlete who uses steroids tests positive. So to do that, we did 0.20 times 0.95. That's 0.19. So interpret this probability in context. This would mean that if you tested many athletes, 19% of them would be steroid users who test positive. All right, this next question is from Unit 6. So it says a player pays $2 to play a casino spinner game. The player spins a spinner, and whatever region it lands on is what their player wins. What is the expected value of this game? So we need to make a table for this. Remember, your table has 3 rows. The first row is the outcome. The next row is the profit. And the next one is the probability. So in this case, there are how many different outcomes? You can get $0. You can get $1, you can get $2, and you can get $10. So there's 4 different outcomes. And then for the profit, we have to subtract the amount that you pay to play. So you're paying $2. So if you land on 0, you lose $2. So it's going to be -2. If you land on 1, you're going to lose $1. If you land on 2, you have a profit of $0. And if you land on 10, you have a profit of $8. So in terms of the probability, we have to realize that not every region is of equal probability. So landing on 0, there's 2 sections that are both 1/4. So that means the probability of landing in that section is going to be 1/2. The probability of landing on a 1, well, if we divide this equally, we can figure out what section that is. That's 1 section out of a total of 8 sections. So that's going to be 1/8. If we land on a 2, that's going to be 1/4. And then landing on 10th is also going to be 1/8. So now to find the expected value, then remember the way that you calculate it is you multiply the profit times the probability. So it's going to be -2 times 1/2 plus -1 times 1/8 plus 0 times 1/4 plus 8 times 1/8. So you're going to multiply the profit times the probability for every outcome and add those all together, and that gives you -0.125. So that expected value interpreted is if you played this game many times, you will lose $1 or 0.125 per game, so about 13 cents per game. All right, the next question is a hypothesis testing problem. Talks about a college professor suspects that the students at his school are getting less than 8 hours of sleep a night on average. To test his belief, he asked a random sample of 28 students, how much sleep did you get last night? Gives us the data here. So we want to know, does it provide convincing evidence in support of the professor's suspicion? So we're going to do all 5 steps. So step 1, we're going to just identify the symbols. So in this particular problem, mu is going to be 8 hours. S, so we need to put this data into GeoGebra, and when you do, you get S is 1.981 hours. Our sample size is 28, and X bar, in this case, our sample mean is 6.643 hours. All right, step 2 is the hypotheses. So HO is going to be mu is equal to 8 hours. And then HA is going to be mu is less than 8 hours, since he suspects that they're getting less than 8 hours of sleep, where mu represents the mean hours of sleep the students get per night. All right, step 3 are our conditions. So the independent condition is big N, which is all students, is greater than or equal to 10 times little n, so 280. That's reasonable to assume. Our sample size, 28, is not greater than or equal to 30, so we're going to look at our normal quantile plot. So when we put this data into GeoGebra, the normal quantile plot is roughly linear. And then for the random condition, it does say a random sample, so that's stated. All right, step 4 is the calculations. So in this particular problem, we are using t because the problem's about means. Sigma is not given, and our sample size is less than 30. So we're going to use t. So it's going to be 6.643 minus 8 divided by 1.981 over the square root of 28. And that gives me negative 3.625. So then you're going to go to your t table. Degrees of freedom are going to be 27, since that's n minus 1. And you're going to look at your table and see what your p-value is. So if you look at your table, your p-value is going to be between 0.0005 and 0.001. So that's definitely less than alpha. So then my conclusion in context, I'm not going to write it because I'm too lazy to write it, is going to be, since our p-value is between 0.0005 and 0.001, this is less than alpha, we reject our null hypothesis. We have convincing evidence that the mean hours of sleep students at the college get per night is less than 8 hours. All right, so for this last example, instead of me writing out the answers, I'm just going to read through the answer key that I have. So, study followed a random sample of 8,474 people with normal blood pressure for about 4 years. All the individuals were free of heart disease at the beginning of the study. Each person took the Spielberger Trait Anger Scale test, which measures how prone a person is to sudden anger. Researchers also recorded whether each individual developed coronary heart disease. This includes people who had heart attacks and those who needed medical treatment for heart disease. Here's a two-way table that summarizes the data. So we have the people who have coronary heart disease, their level of anger according to that test, and then people who don't have coronary heart disease and their level of anger according to that test. So we want to know whether there's good evidence that one's anger level based on the anger scale test is associated with one risk for developing CHD. So this is going to be a chi-square test of association. Starting with step 1, your hypotheses. So in a chi-square test of association, your null hypothesis is that there's no association between the two variables. So no association between anger level and someone's risk for developing CHD. Your alternative is that there is an association between those variables. Step 2, you're going to do your expected counts. So remember, to do the expected counts, you have to do the row total times the column total divided by n. So here we have the row totals and we have the column totals. So the expected count for low anger CHD, we would do 190 times 3110 divided by 8474. That gives me 69.73. So moderate anger, the row total is 190, the column total is 4731 divided by 8474. That gives me this, etc. for the rest of these columns. So now that we have the expected counts, we can do our conditions. So the independent condition, all people with normal blood pressure is greater than 84,740. That's definitely reasonable to assume since we sampled people who had regular blood pressure. All the expected counts are greater than 5, and it does state that the sample is randomly selected. Okay, so now for the calculations. So to calculate the chi-square test statistic, remember that what you need to do is you need to take the observed count minus the expected count squared divided by the expected count. So for every single cell in here, the observed count was the original table. You're going to do the observed minus the expected squared divided by the expected and do that for each one. Remember, you can do that in GeoGebra. Once you have each of those and you add them all up, and you should get a total of 16.08. That is your test statistic. So the chi-square test statistic is 16.08. To get your degrees of freedom, it's row minus 1 times column minus 1. So there's 2 rows and 3 columns. So 2 minus 1 times 3 minus 1, that's 2. And then you're just going to put that into the chi-square calculator, which is going to give you a p-value of 0.000322. So since our p-value is less than alpha, we reject our null hypothesis. We have statistically significant evidence that there's an association between anger level and one's risk for developing CHD.